what is the decimal equivalent to the binary? So binary number is given. So in the binary number, now this part you have to take it separately and this part separately. That's how you have to work on that. So when we take this one, when we calculate 53 is coming from this part, 53 is coming from this part. So these things you have to calculate. So how to calculate? This is to the power minus 1, this is to the power minus 2, right? So when you write it down, so you can write to the power minus 1 means 1 divided by 2, 1 divided by 2 plus, then 2 to the power minus 2 means 1 divided by 4, 1 divided by 4. So you can write it in another way. 4, here you get 3, right? So 3 divided by 4, so you are getting uh, 0.75, right? So your answer is, now here from here you are getting 53. So your answer is third one is the answer. Then we'll go to the next one. What is the 2's complement representation of a decimal 86? Decimal 86. If an integer represented by 8 bit, now you know that 86 is positive value. So positive values, when you are converting to the 2's complement or 1's complement, you are having the same value. That means you don't want to replace or invert the bits, right? You have the same value. So what you can do is you can convert this decimal value to the binary value. Then if because you have to represent with 8 bit, to make it 8 bit you have to put 0 in front. So your answer will be for the 86 you are getting 1010 110. So first answer is coming. So your 86 we are getting 1010 so it's there, and you have put 0 in front to make it 8 bits. Then we'll go to the next one. Which of the decimal number is equivalent to the 2's complement binary value 1 1? So it is what you have to do is, when you get 2's complement value, you are starting with 1 1 1 0 0 0 1 1 0. So when you see that it is starting with 1, you have to decide it's a negative value. It's a negative value. So what you have to do is, you have to invert bit 0 0 1 1 1 0 0 1. Then add 1 to the least significant bit. Then your answer will be, you have to add that, right? So here you get 0, here you get 1. So other part will be same, that is 1 1 becomes 0, then you get 0 1. Right? So then you have to convert it to the decimal. Then you have to convert it to decimal. Now here, when this binary value 111010, when you convert it, you are getting 58. But this 58 is negative value. It's negative value because we have decided from the question, we have decided it's a negative value. So this is the answer. Then next one, 7e, yes, plus equivalent binary value is given. So binary you convert it to hexadecimal by separating each 4 digit. Then you get 2 and D, right? So 2D is there. Then try to add them together, 7E and 2D. So when you add them right here, I think it's 7E, yes. 7E plus 2D. I'll take it down. So when you add in hexadecimal values, D is 13, E is 14. So when you add them together, see the answers. 27, when you get 27, 116 is there. So you are getting remaining value as B. Then 1 is going front. Then 7 plus 2 plus 1, you get 10. That is your answer will be A and B. Sorry, A B in 16. So this is the answer. So we have done these things if you miss some lessons, you can check our videos. Okay, we'll go to the second part questions. First one, they are asking, show how the computation 5 plus minus 3 is done in 8-bit 2's complement arithmetic. Explain how you deal with the carry generated from the most significant bit. So 5 plus minus 3. So what you have to do is, first find out the 5, 2's complement is a positive. So you can write 0, 0, 0, 0, 0, 1, 0, 1. Minus 3, first you find the 3, 0, 0, 0, 0, 0, 0, 1, 1. Then invert the bits, 1, 1, 1, 1, 1, 1, 0, 0. Then add 1. Then your answer will be, sorry, this one, right? Then you have to add them together. Add them together, that is 0, 0, 0, 0, 0, 1, 0, 1 plus 1, 1, 1, 1, 1, 1, 0, 1. So add them together, you are getting value 1, 0, 0. I will do it on the board. Okay, 5 plus minus 3. Right? So 5 you can write 0, 0, 0, 0, 0, 1, 0, 1. Minus 3, you can write 3, then convert to other side, invert bits, then add 1, 1, 0, 1, 1, 1, 1, 1, 1. Then you are going to add these two. So your answer will be 1, 1 becomes 0. Here you get 1. Here you get 0. These all are zeros. And this is 1. Right? So you are getting 9 bits. So 9 bit. So what we can do is, when you get 9 bit, when we want to represent with 8 bit, you just ignore and you have to mention ignore carry bit or MSB. So your answer will be this one, right? That you have to mention. The question they are asking, how you are dealing. How you are dealing means you have to mention that your carry bit, you are going to ignore that, right? So that's you have to tell. Okay, and then next one, describe how you would determine whether given positive integer. No, don't do that. That is related something else. Yeah, determine. Yeah, determine. You can determine whether given positive integer odd or even. Odd or even when you are dividing by two. If your remainder is 1, it is odd. Otherwise 0. Even. That means if your remainder is 0, definitely it's a even. Otherwise it's odd. That you have to mention. Then show how the computation 15 plus 5 minus 5. So same way, I will just type the answer that what I did earlier. The same way, you have to convert the 15 and minus 5 into binary. 0, 0, 0, 0, 1, 1, 1, 1. So minus 5, find out the 5 and add invert the bits. Invert the bits, that is 0, 0, 0, 0, 0, 1, 0, 1. Invert the bits. And add 1. So your answer will be 1, 1, 1, 1, 1, 0, 1, 1. Then add them together. Your answer will be 1, 0, 0, 0, 0, 1, 0, 1, 0. So they are even. What you have to do is you have to ignore this carry bit or more significant bit. That's you have to mention. Okay. We'll go to next part. Convert decimal 13 and decimal 19 into 2's complement number. Use 8-bit. They are also the same way. 13 means it's a positive, so you don't want to worry about that. You just convert it like this, like a binary. Minus 19, you have to 16. Yeah, right. So then invert the bits. Then add 1. So this is the answer. Then compute decimal 13 decimal minus decimal 19 by using 2's complement. So even this you have to subtract. What you can do is you have to add them together. So 13 plus minus 19. Give the answer in 2's complement form. So what you can do is you can add them together. Plus we have found right. So add them together. The answer will be I'll write the answer. Yeah. Here you get 0, then it become 1. The rest of that will be same. Okay? So this is your answer. We go to the next part. explain how the positive and negative numbers 2's complement can be converted into decimal numbers. So what you can tell is check whether you have the uh, same answer here. um, you have to check the most significant bit whether it's a 1 or 0. If it is 0, it's a positive value, just convert it to decimal value by using 2 to the powers. If the first value, that is most significant bit, is 1, it's a negative value, so flip the bits and add 1 to the least significant bit and convert it to decimal and keep it as a negative value that you have to mention. Show the negative 001 is 111. Note that both numbers are represented in 2's complement. So 000 means it's actually 1. It's a positive 1. So you are getting 1111. Both are in 2's complement. So 2's complement, if it is C, that's what I told earlier. If you get 0, more significant bit is 0, you can just convert it to decimal. That's 1 is coming. If it is 1 means you have to invert the bits 00000 and add 1 to the least significant bit. Then you get the value 0001. It is but it is negative value. So same, so that you have to mention, then you can prove that. So negative of 0001 is 11. That means you are getting the same value, right? When you convert, you are getting 1111, right? Okay, next part. Assume that the particular digital device integer are represented 8 bits. 2's complement form. However, the result of computation are printed in decimal. So give the representation of 10 in the above. So 10 is that now in this device they are telling it's in 2's complement form. So 10 means it's a positive 10. So you can write 1010. Give the representation of 25. So 25, you find it 25. Uh, 000. It's like this. Then invert the bits. Then add 1. So your answer will be 11100111. Well, that you had mentioned. Next part. Explain how the computation of 10 minus 25 done by the device by using your representation given in section. So explain how the computation. So what you can tell is you have to add them together. So even you have to subtract here, you have to add them together. Then I'm not going to do that the same way. List the steps necessary to transform result obtained in section about to decimal form from in order to print the answer. So what you are getting, you have to convert it decimal. So what you can do is you have to explain. That means you have to check the most significant bit. If it is 0, just convert it to decimal. If it is 1, invert the bits, add 1 to the LSB and convert it to decimal and keep it as a negative value. Okay, next one, write down the two's complement representation of 2, 12 and 8. So these things the same way. If you have any problem, tell me. If you want me to explain anything, මේවා ටිකේ මොනවා හරි explain කරන්න ඕන නම් කියන්න. Computer, yeah, same thing. 68 or system. Here state one advantage of using two's complement representation for data in internal operation of computers. There you can write. So you can write a single representation for 0. So it's not confusing. If you are using one's complement, you are getting two different representation for 0, positive 0 and negative 0. But in two's complement, you get only one. So that is kind of advantage or um, for the internal operation, because you have one value for the 0. And subtraction also carried out as addition. So more efficient calculations you can write down. Then list the four method of character representation: BCD, EBCD, IC, ASCII, and Unicode. We have discussed. What is the advantage of and disadvantage of using BCD? So BCD advantage is you can represent numbers and into decimal numbers very easily. But BCD disadvantage is you have only 4 bits, so you can represent numbers very limited data with that. We have discussed them last week. What advantage does Unicode have over ASCII? So, Unicode is actually a universally accepted, uh, and it's supporting for all the codes or more symbols. Like it has like 65,536 characters can be represented. So ASCII you don't have that much of space to represent. So EBCDIC even advantage, you can represent more characters than ASCII, because you can around 256 characters you can represent. Then but disadvantage is it cannot represent more languages, only few, and it doesn't have linear sequence even now. ASCII, if you know letter A, you can go to letter B quickly like that. But here you don't get, right? Okay, that's all for the unit 3 parts. So we'll move to the unit 4. Okay, write down the topic. Write down the topic. New topic, unit 4. Unit 4. Logic gates and digital circuits. Logic gates and digital circuits. Under that, write down logic gate is an electronic component. Logic gate is an electronic component that performs basic logical functions and it can be identified It can be identified. It can be identified as a fundamental building block of a digital circuit. Fundamental building block of a digital circuit. Fundamental building block of a digital circuit. Each logic gate has a unique symbol. Each logic gate has a unique symbol. Unique symbol. And a unique logical function. And a unique logical function. A gate can have multiple inputs. Inputs keep at the end, multiple inputs. And only one output. Output I'll show you. Only one output. An input can take 0 or 1 at a time. An input can take 0 or 1 at a time. Zero, 1 at a time. Inputs are processed according to the logic gate and according to the logic gate and output is provided according to that. Output is provided according to that. We'll see. So what are the logic gates that we have and how they are working? So when we take a logic gate, I told you they have different types of symbols, right? And you have inputs and output. Now as example, if I take this kind of a circuit, this is a small circuit inside the computer, I take logic gate, right? This side you have inputs. This side you have output. So input you can have either one input, 2, 3 like that. You can have several inputs even, right? But all the time, you have only one output. Remember that, right? So according to the logic gate inside this box as example, alright? According to the logic gate inside this box, it is processing. So So whatever you can input, you can input either 0, 1, 0, 1, because you can't have other values, right? So whatever you are giving here will be processed what is inside this box and giving the output according to that, right? So if you have one input, how many output you can generate? If you have two inputs, how many outputs you can generate? That like that you can calculate how many patterns are there. So that is called truth table. In the truth table, we represent what are our inputs and what we can take as output, right? So if we have one input, right? So you can have either 0 or 1. If you have one input here, only one line, that means it can go either 0 or 1. You can't have both at once, right? So either 0 or 1 is going, right? If you have two inputs, like this, A, B, something like this, A, B, O, X, Y, whatever, two inputs, you can have 0, 0, you can, like, you can transmit with the, using these two lines, then 1 becomes 0 and that another one, the 0, 1, then 1, 0, 1, 1. That means if you have two inputs, you can have four patterns, four input patterns you can insert to this logic gate, right? If you have three inputs like that, three inputs, so you can write like this, then you are getting eight patterns, eight output patterns. If you have four inputs, you are getting 16 output patterns. 16 output patterns. Sorry, 16 input patterns as well as output patterns. Both the number of input and output patterns will be same. Input patterns will be same. So how to find that? You can take 2 to the power n. So I will take n. N is number of inputs. N is number of inputs, right? So as example, if you have one input, 2 to the power 1, 2. Two patterns you can represent. If you have two inputs, 2 to the power 2, 4 patterns. If you have three input, 2 to the power 3, 8. If you have four input, 2 to the power 4, 16. Right? Like that. A number of inputs and give how many patterns are there. Right? I think you can understand that. If you can you take this down, like this is the input, this is the logic gate, this is the output. Only one output is there, and try to take it down quickly. Number of inputs, how to get that number of patterns even. Okay, right? So we'll see. So what are the logic gate that is coming here, and what are the patterns we can represent? So remember, you have to memorize. You have to memorize all these logic gates, symbols, their patterns, truth tables, and the circuits. So without memorizing that part, it is difficult you to understand how this is this kind of circuits are planning happening. So it will be difficult if you can't remember, if you can't memorize these gates, their symbols, and the truth table especially, right? So we'll go through each gate. Some of you, if you have done O-level ICT, you have done around 5 gates, but here we are going to discuss 7 gates for the A-level, right? So first one I'll take here, I'll take AND gate, right? The symbol is like this. I am taking only 2 input gates, so you can have several inputs even, the same pattern, same thing, but you have only one output, right? So if I will take A and B as my input, A and B as my input. So if you input A, B, you can write the output as A dot B, A dot B. Now, if you don't see this circuit, if you don't see this gate, if you see A dot B, there you can understand A and B has connected with the AND gate. So AND gate can be represented with the dot. Even you don't have a dot, A, B even that's the same. That's the same, right? So I will write the truth table here. So two inputs. So I can write 0, 0, 0, 1, 1, 0, 1. Your output will be 4 outputs are coming. I will draw a small circuit for this one. Small circuit for this one. You have a bulb, then small batteries. Then you have 2 switches like this, right? 2 switches. You take A and B. Same. So 0 means off, 1 means on, right? So 0, 0 means both switches are off, so your bulb won't work. So you can put 0. One switch is on, but other switch is off. Still, your bulb won't work. Here also not work. Both switches on, that will work. That means your output will be 1. So it's like you can, when you are memorizing, you can memorize this AND gate like a multiplication. So 0, 0 multiply 0, 0, 1 multiply 0, 1, 0, 0, 1, 1. So whatever the way it's possible for you to memorize, you have to memorize gate, symbol, and this logic circuit. And this thing also, that the circuit even you have to memorize, because sometimes they are asking, giving this kind of a picture and asking what this gate represent, right? Okay, take it down and gate, take it down, everything. Okay, I think you have finished that. We'll check next one. That is O gate. O gate symbol is looks like this. Your output will be A plus B. Your output is A plus B. So I will draw the circuit also here. Your switches will be like this, A and B. So same way, zero, you can put zero for off, one for on. So both switches off, bulb won't work. So it is zero. One switch is on, that is power is going, that is circuit is complete. So your output will be one, here one, here one, right? So take it down also. This is for O gate. Okay, we'll see next one. Next one, not gate. Not gate. So it is bit different because you have only one input, or you have only one input here. Now usually we are in earlier gates we can have either 2, 3 or more than that inputs even, but here only one input is there. But earlier gates you can't have one input, at least you have to have two inputs or more than that. But here you can have only one input, you can't have any other input. So input is, if you input A, you are getting A dash. So sometimes when you're writing, you can write A dash even, same way. So if I write inputs, it can be either 0 or 1. So 0 become, I'll draw the circuit, then you can understand this one. So here it's like this. I put the switch like this, then batteries, right? So I put a small resistance. This is called resistance. So when you put the resistance, your current flow in the current will be like having get some resistance. So if you this switch will take as A. If the switch is off, your light will work. One. When the switch is on, what will happen? The light won't work because the current is going the path where you get the less resistance. Here you have resistance, so it is not going to this side. The current is going flowing this path, so your light won't work. So your output will be zero. Output will be zero. Okay, take it down. That is not gate. Okay, we'll see another gate. This is called Nand Gate. Nand. Nand Gate. So it looks like this. So if you input AB, your output will be A dot B whole thing dash. Actually, it contains AND gate and not gate. By using and not gate, it has developed. So if you get here, you get A dot B. When it goes here, A dot B dash. That's how it has composite. Uh, okay. So if you take to table, before I write the output, I'll show you how this gate can like practically works, right? So if you have batteries like this and two switches, here I'm connecting the bulb with a resistor like this, right? So you take switches AB. So both switches off, bulb will be working. That is one. One switch is on, so power is not going through that one. Definitely it is going this side. One. Both switches on. Uh, what will happen now here? Switches A and B is there. So here you have a resistor also, right? Here you have a resistor also. Because of that, power or current is going through this one because there's a resistor here. So power is not going through that one. When you both switches on, that current is flowing through these circuits. Then bulb is not working. So this bulb is not working. So 1 it become 0. So actually this is the other way of AND gate. So if you can remember the AND gate, you can easily remember NAND gate because this is other side of AND gate. So AND gate, I think you can remember 1 it become 1, but others became 0. But here all are ones, 1 becomes 0. This is called NAND gate. Take it down, circuit and the truth tables. Okay, we'll see next one. This is Nand Gate. Uh, Next one, no gate, no. Looks like this. So if you input A, B, your output will be A plus B dash, A plus B dash, right? So here truth table, we'll see how this truth table is coming. I will take some this is our circuit. This is our circuit. So here I am using the bulb with a resistance. I'm connecting like this, right? So both switches off, the bulb will be working. Bulb will be working. So your output will be 1 here. So when the switch is on, the power, the current is going the path which has a less resistance. So because of this resistance, the current flows this way. So your bulb won't work. So it become 0. So these all become 0, right? So these are the two switches, A and B, right? So actually it is other side of the O gate, other side of the O gate. Okay, take it down quickly. Okay, we'll see next one. Now these five we have done in all your C1. These five we have done in all your C1. So this is a new thing for A level. XO gate. XO gate, right? Right? So the circuit or the drawing is looks like this. So if you input AB, your output will be A plus you have circle and B, right? XO gate. So I will show you how this circuit is working for this one circuit. I will take a bulb, batteries and all that, like the earlier one, Take the batteries here and the bulb here, and now my switches like this. I have switches like this, right? So this switch, either this is 0, this is 1, that is switch on and off, right? So here, this switch, if you put to 0, right? And other switch also put to 0, the circuit is not connecting. Because both switches you put to 0 or off. 0 say will take off, 0 I put it off, 1 is on, right? If this switch connect to the 0 side, that is both 0 side, this circuit is not completed. So that you get 0. One is off, other one is on here. So you can see current is flowing here and it is coming here and that is completed. So you are getting 1. That is bulb is working, right? The other way around. This become 1, this becomes 0. So power is, that is current is flowing. So here also 1. If both switches on, that means this connecting here and this also connecting here. But they are not connecting, the circuit is not connecting, so you are getting C. So that is for XO gate. XO gate. Take it down. Okay, we'll see next one. This is called XNOR gate. XNOR gate. Gate's symbol is looks like this. Actually, it is connecting XOR gate and NOT gate. That's how you generate the XNOR gate. Your output will be like this. So your circuit, I will show you how this can be connected. So you have the switches like this. If you are getting 0, 0, this is 1, 1, right? So if both switches are 0, the circuit is completed. This is working. That means 1. So 1 is 0 and other one is 1. You don't circuit is not completing, so it is 0. Here also 0. If both switches 1, that is this side, both switches coming like this, circuit is connecting, your output is 1. Okay, take it down quickly. Okay, we'll see. Now these are the basic and the uh, combinational gates. So from these gates, you are getting different type of questions, different types of question. One type is you are getting the circuit and asking the expression. Asking the expression. It's like this. So if I draw something like this, AB, and I'm taking same AB here, then I'm connecting with AND gate. So what is the expression of this gate? What is the final expression of this gate? So this type of question can come. So one method. So each gate, first you write the output from each part. That means here you are getting not gate. Here you have dash, a dash, right? So no need to write each and every part, but this is the method of getting the correct expression. So if you can write it at once, doesn't matter, right? Here a dash. So it's an AND gate. Here you are getting a dash dot b because we know that the AND gate you can present with a dot. A dash dot b. Here it's a no gate. So a plus b dash. A plus b dash. So your final output I can write here a plus b dash. Then here this side you are getting a dot b. A dot b. This gate is an AND gate. So AND gate, because of the AND gate, you can put a dot here to connect those two. So it's better if you can put brackets like this, then it will be more clear, right? Write down like this. Write the question, write down. Find out the Boolean expression. These are called Boolean expressions. Find out Boolean expressions for the following circuits. For the following circuits. Okay, take this down as an example. I'll give you more. Okay, I think you have finished that. I will share some questions, then we will start that kind of question. So you are getting this kind of a circuit and you have to find out what is the Boolean expression, final Boolean expression, right? I will share some questions. Okay, try to find out the final output of these logic circuits. After finishing, you can type and send me the expression through the chat. So when you're typing, you can use that apostrophe instead of a dash. Okay, try it out. There are 4 questions. I will write the answer for the first one. So when you're writing, I will use apostrophe for the dash. So here you can write A plus, here you are getting B dot C. I will put it within bracket B dot C. Then again I will write B dash. Here you are getting B dash and A dot A. So that is with a Nand gate. Because of that, I'll put dash again here. It's like this. Then all together, you are getting this part. From here, you are getting B dash dot A with the final gate is a no gate. Final gate is a no gate. So this one actually, I will write it here. So this part. And B dash dot A dash, you are adding with plus. Then again all together it's a dash because it's a no gate. It's a no gate. Try it out. Others try them out. So you can without dot even you can write, but I will write dot plus A dot B dash dot C plus A dot B dot C dash plus A dot B dot C. Without dot even you can write this and gate, doesn't matter. Okay, you have sent me the answers. Some in there, okay, correct. Without dot even you can write, doesn't matter. And gate you can represent like that. Then third one here. Yeah, I can write y dot x dash plus y dash dot x. Easy one. Last one, try it out. Send me the answers and others. Okay, last one we can write here. We are getting three inputs: a dot b dot c. That is, I will write a b c without dot even, doesn't matter. I told you. Plus, so other part I can write like this. Here a dot. Again, I will put a bracket here because b dash and c dash is coming from there. B dash plus c dash. You have to bracket. Yeah, right. So when you are using bracket, you put it properly. Yes. Okay. Okay. Dini also has sent some in there. Okay. Right. These are the answers. Okay. So next week we'll continue. Now this is how, when we are getting a circuit, how we can write the expressions, right? So we have something, we are getting the expression and we have to draw the circuit, and we are getting the expression, no, this kind of thing, and we have to find out the truth table, right? These kind of calculations are there. Okay, we'll finish for the day. Next week we'll continue from this part. Okay, thank you.